With this section of work, it's really important that you get the details right. You cannot call an intermolecular force a bond, and you cannot call a bond an intermolecular force. So please be very, very careful about that, and you will not get marks in the IEB exams if you do that. So let's try and look at the details. The molecule in the diagram shows part of the atomic lattice for diamond, in which each carbon atom is bonded, not intermolecular forced, bonded to 4 others to form a huge molecule, one big molecule containing many millions and millions of carbon atoms. Define a covalent bond. The definition of covalent bond includes the concept of the sharing of electrons. So you need to say something about 2 nonmetals, and then you need to say that they share electrons. Those are the 2 things that get you marks, and bonding is a process which attempts to lower the energy of particles. Explain, not just say to me it has a high melting point or there are lots of intermolecular forces. There aren't lots of intermolecular forces, there are actually lots of bonds. Okay, so explain why diamond has a high melting point. The first thing you need to say is it is an atomic lattice. And we discussed atomic lattices, and you only need to know about diamond and graphite. There are very few you need to know as well. All covalent bonds, lots of energy to break up the lattice. How you articulated this also counted for some of the 2 marks, and sometimes you got 1.5 if it kind of came out as some jumbled, garbled mess. 1.2, the crystalline structure of a cubic form of boron nitride, Bn3, is shown alongside. Define the term electronegativity. Well, we've had this so many times, I think everyone got it right. It is the measure of the tendency of an atom to attract a bonding electron pair. If you say it's a bonding electron pair, it's obviously in the bond already. And you have to have an electron pair, not just one electron. Using Pauling's scale of electronegativities, that's this electronegativity on the table, determine the nature of the intramolecular bond which occurs in boron nitride. Well, they've told me to go to the electronegativity scale. So boron's electronegativity is 2, nitrogen's electronegativity is 3, therefore the electronegativity difference is 1. You can't just say, so the electronegativity is 1. It's not. It's a difference between 2 electronegativities, and then you can say, therefore, polar covalent. Some of you said that boron was a metal and nitrogen was a non-metal. Boron's not a metal. Boron is on the line of the staircase, so it is a semi-metal. So it can behave either as a metal or a non-metal, and due to this electronegativity difference, it is polar covalent. Then it says the table shows the melting points of sodium chloride and magnesium oxide. Those are both big numbers. Explain why the melting points are so high. These are both ionic. Lots of energy required to break electrostatic force between ions. Right, Karen. You then get this table where you can clearly see water is anomalous. In other words, it doesn't follow the trend. But the melting point gets higher and higher and higher as you go down group 6 with sulfur, selenium, and tellurium. You are then able to say, well, they want you to justify why this has such a high, well, relative to the others, such a high melting point. Let's see what they ask. Name the specific intermolecular force that exists in hydrogen sulfide. Now, hydrogen sulfide is 2 nonmetals. It is a polar covalent molecule, but that's not what they're asking. They are asking for the specific intermolecular force. What holds polar covalent molecule to the next polar covalent molecule? A dipole, dipole intermolecular force. And you have to be specific because they say it's specific. And then water is again a polar covalent molecule, but it has a special, because it's H2O, or if it was NH3, or if it was HF, those are the only three molecules you need to worry about that have a special type of intermolecular force, and that intermolecular force is hydrogen bond force. Hydrogen bond force. Explain how a hydrogen bond force is formed. Now, it's asking you how it's formed, not what it's made up of. I was overly generous in marking this, so be very aware of that. The first thing is that you can explain a little bit about what makes it up. It is a small, high electronegativity atom bonded to hydrogen. That makes the molecule. Because this is small and a strong dipole, molecules get close and attract strongly, therefore anomalous, in other words, out of the sequence, anomalously high melting point and boiling point. That wasn't what the mark was all about. You land up with a strong intermolecular force. Explain how the hydrogen bond force is made. You could have told me that. And then you need to differentiate between the bonded molecule and the strong intermolecular force that exists between it, which is then H, hydrogen bond force. Consider those three and explain why this one has got the highest boiling point of the three compounds. It's the biggest. Big molecules have more electrons, therefore more electron cloud wobble. Therefore, they are able to attract each other more strongly, therefore stronger IMF. Weird thing happens over here. Why? Because it has a very tightly held together molecular lattice with a very strong electronegativity to form a very polar molecule. But generally speaking, the bigger the molecule, the greater the intermolecular force. Now we've got an exothermic combustion reaction. It's a burning reaction, and it's represented over here. They balanced it and everything for you. Differentiate between exothermic and endothermic. You did that very effectively. Exothermic is the releasing of energy. Endothermic is the taking in of energy. Sketch this fully labeled potential energy profile graph for a combustion reaction. The very first thing you do with any graph is you label the axes. And in this graph, it's the potential energy versus something called the reaction coordinate. If you gave me time, I'd accept it. I'm not great with that, but reaction coordinate is better. I then draw my classic exothermic shape, and that most of you got perfectly right. And then you have to label the following things. It is the activation energy. It is energy from there to there is the activation energy. I'm shorthanding here, so forgive me. Then the delta H value is from the difference between the products and the reactants. You need to show that quite clearly. Then they want the energy of the reactants, which is this line over here, the energy of the products, which is that line over there, and the activated complex. You must follow the instructions very, very carefully. The activated complex is a point, whilst the activation energy is a range. Then it says draw Lewis structures of the following. types of bonding between atoms in a molecule and the lone pairs of electrons, by now you're expected to know the shapes of molecules and to represent them properly with Lewis dots. So I was quite strict in marking this, so watch what happens. You are expected to know that you've got a tetrahedral shape with methane. You are expected to know that there is one shared pair here with each of them. You're expected to know oxygen shares 2 pairs of electrons. You are expected to know that you have got a double pair of electrons on each of those oxygen molecules, so there and there, there and there. You're expected to know that carbon dioxide is a linear molecule with 2 shared pairs between the carbon and the oxygen. You're expected to know that water is a angular molecule with 2 lone pairs and 2 shared pairs. That's what you're going to need to do to get all of your marks. Then we go on to a bond energy question. Watch carefully. So given those bond energies, first thing is what is the bond energy in one methane? There were 4 HC bonds. So it's 4 times 413, which is equal to 1652 kilojoules per mole. Then you have got in one carbon dioxide, there are 2 double CO bonds, so it's 805. And you've got kilojoules per mole again. And finally, bond energy in 2 water molecules, so it's 2 times 2 times 464, because there are 2 carbon, at least oxygen, hydrogen bonds, so that's 1856 kilojoules per mole. And you've been given this piece of information already. Using your answers, determine that what delta H is. Delta H is going to be 996 plus 1652, the energy I put in, minus the energy I get out, and I land up with minus 818 kilojoules per mole. This question comes from last year's final matric exam, so it's important that you get used to this sort of wording. Name the specific type of bonding that is present in a molecule of hydrogen chloride. That's HCl. It's 2 non-metals. They have got an electronegativity difference between them, 2,1 and 3, so it's 0,9. And therefore, but all they asked for, what is the type of bonding? It is polar covalent. The next thing is, again, make use of this idea of Pauling scale of electronegativities as provided on the periodic table to explain. So you have to explain the types of bonding found in hydrogen chloride and in calcium chloride. You've got to use the electronegativities. So you need to say that in hydrogen chloride, my electronegativity difference, not the electronegativity difference is 0,9. My electronegativity difference in calcium chloride turns out to be 1 and 3, so it is a difference of 2, and therefore I have got over there a polar covalent, and over here I have an ionic. It seems a little repetitive, but it is the explanation that gets you the full 4 marks. Hydrogen chloride molecules are described as dipoles. What does that mean? It means that the molecule has, you could say, an electron cloud wobble, you could say an uneven electron cloud distribution, but I would accept a slightly negative and a slightly positive side. Calcium chloride dissolves in water, is soluble in water. The structure of its crystal lattice is broken down by the water molecules to form aqueous ions in solution. Name the type of crystal lattice in calcium chloride. Your mark came from saying that this was an ionic lattice. Remember, there are 4 types of lattices. There is an atomic lattice, there is a molecular lattice, a metallic lattice, and an ionic lattice. So ionic has 2 meanings. One is that it's a type of lattice. The other is that it is also a type of bond. Metallic and ionic both do that. With a covalent bond, you don't get a covalent lattice. Well, you do. An atomic lattice is a covalent lattice, but then you also, from a covalent bond, get a molecular lattice. Use diagrams to illustrate your answer and explain. Explain means you have to use some words. You can't just give me pictures. How does the crystal lattice of calcium chloride broken down during the dissolving process? So you need to say that a polar covalent molecule attracts the ions out of the lattice with an ion dipole intermolecular force. Then draw a positive ion with the water molecule orientated. Let's look at water just for a second. It's got the O and it's got the H's. The H's have got an electronegativity of 2,1. The oxygen has an electronegativity of 3 or 3,5, but a fairly high electronegativity. That means that the oxygens are slightly negative. The hydrogens are slightly positive. So many of you reverse that around. So you need to have the hydrogens orientated towards the negative ion and the oxygen orientated towards the positive ion in your picture.